Okay, so hi everyone. My name is Afika binti Akasha, and for the video today, I am going to teach you on 5 basic assembly language instruction in regarding the subject of PHY4301, microprocessor and microcontrollers. So in this video, I will be talking about data transfer instruction. Secondly, arithmetic instruction on ADD and SBB. Next is bits manipulation instruction. Number 4 is interruption instruction. And number 5 is program execution and transfer instruction. So let's take a look at the first basic assembly language instruction. So we have data transfer instruction. In this particular video, I'm going to focus on the MOV. It is an instruction to transfer to Word. So let us get to know on what is data transfer instruction. So basically, data transfer instruction is the instruction used for transferring data from source to destination. And the operand can be a constant memory location, register, or input-output port address. As I said earlier, I am going to focus on MOV instruction. So what is MOV? MOV is an instruction used to copy the byte or word from provided destination. So for MOV instruction, which I said earlier, it copies the data item referred to its by second operand. For example, register, content, memory content, and constant values. So for it will be into the location that refers to its first operand, which is the register or memory, while register moves are possible and direct memory to memory moves are not. So the description of this instruction is copy operand 2 to operand 1. So the MOV instruction cannot set the value of the CS and IP register. The copy value of one segment register to another segment register and copy immediate value to segment register. So the algorithm used for MOV is operand 1 equals to operand 2. In cases where memory transfers are desired, the source memory content must be first loaded into a register, then can be stored to the destination memory address. So the syntax for this particular instruction is reg memory, memory reg, reg, memory immediate, and reg immediate. So how to write it can be can look as follow. At the picture insert on the slide, that is how we can write it on our emulator. So, okay, here's a short programs that demonstrate the use of MOV instruction. So basically, this instruction can be used to emulate, and we can get the output on the emulator screen as shown on the slide. Let's move on to the second instruction, which is the arithmetic instruction. So arithmetic instruction used to perform arithmetic operations such as addition, ADD, subtraction, SUB, multiplication, MUL, division, DIV. And there are actually more than this basic operation. There are increment, INC, decrement, DNC. So there are actually more operations. But for this case, I am going to focus on ADD and SUB instruction. So basically, ADD and SUB instruction used for performing simple addition or subtraction of binary data in byte, word, and double word. So in example, for adding and subtracting 8-bit, 16-bit, or even 32-bit operands respectively, the ADD or SUB instruction can take place between register to register, memory to register, register to memory, register to constant data, memory to constant data. So memory to memory operation are not possible by using ADD or SUB instruction. And ADD or SUB operation sets or clears the overflow and carries flag. So the syntax for ADD and SUB instruction is ADD slash SUB destination source. Okay, for this one is 8086 emulator ADD instruction. So this instruction adds the data of the destination and source operands and store the result in the destination. So for both operands, it should be of the same type. For example, words or bytes. Otherwise, assembler will generate an error. So for ADD instruction, it support these following operands. So if the source is register, the destination would be register. And for the example, we have ADD AXPX. And then for if the source is register, the destination will be immediate. And example as follow. If the source is register, the destination would be memory address. And the example would be ADD 204CH ALDD BPSI plus 23DX. And for memory address, the destination would be register. Example, ADD CL BX plus 15. So if let's say the sum of two operands exceeded the size of destination operand, then it would set the carry flag to 1. And the ADD instruction can affect AF, CF, OF, PF, SF, and ZF. So ZF flags. So depending on upon the result, if the result is 0, then ZF is equals to 1. Negative result sets SF equals to 1. So these are the assembly codes that we can use to put in our emulator to emulate and run to see the output. So this is the output that we will get for these following assembly codes. So for subtraction instruction, so this one is for subtraction instruction without carry. So basically, subtraction instruction takes two operands, subtract the data in the source operand from the data of destination, and then store the result back to the destination operand. Just like ADD instruction, both operands should be either in bytes or words only. So if let's say one operand is in a byte and another one is in words, then insert 2 zeros at the start of the byte, but they should be of the same type. So the subtraction instructions support the following operand. So register to register, register immediate, register memory address to register, and example as follow. So these are the assembly codes and the output that can be used to emulate and run on the emulator. So basically, over here we can see that the SUBAX BX instruction subtracts BX from AX and then store the differences in AX, which is AX equals to 9CA minus 66F minus 35B. So in the next instruction, SI is loaded with 0700H, and then the sixth instruction, SUB SI, AX subtracts AX from the data stored at the memory location DSSI and stores the different at the same memory address. Okay, now we are going to take a look on the bits manipulation instruction. So what is bits manipulation instruction? So basically, bits manipulation instruction used to perform operations where data bits are involved. In example, we have operations like logical, shift, and many more actually. So for this particular instruction, I am going to focus on logical operation, which is not and OR. So for not instruction or not destination, the not instruction inverts each bit of a byte or a word that destination can be register or a memory location. So flags, the not instruction affects no flags at all. So the example as follows. Next, let's take a look at AND instruction. So for AND instruction, AND destination and source. So instruction, this instruction logically, how do we say? This instruction logically A and D's each bits of the source byte or word with the corresponding bit in the destination and stores results in the destinations. So the source may be an immediate number, a register, or even a memory location. So the destination may be a register or a memory location. So the source and destination of the source and destination both cannot be memory locations in the same instruction. So if let's say the CF and OF are both 0 and after A and D, the PF, SF, and ZF flags will be affected, and therefore AF will be unidentified and undefined. So the example as follows. Next, let's take a look at the OR instruction. So for OR instruction, we have OR destination, OR source. So this instruction logically ORs each bits of the source byte or word with the corresponding bit in the destination stores result in the destination. So the result may be an immediate number, a register, or a memory location. So for the destination may be a register or a memory location. The source and destination both cannot be memory locations in the same instruction. The CF and OF are both 0 after OR, and the PF, SF, and ZF are affected. Therefore, AF will be undefined, and the instruction as follows, and the example as follows. So let's move on to the next instruction, which is the interrupt instruction. So basically, interrupt instruction, it is an instruction that are inserted at a desired position into the program to create interrupts. So it can be used to test the working of various interrupt handlers and it includes INT, which is the interruption instruction with type number, INT3, breakpoint interrupt instruction, or INTO, interrupt on flow instruction. So for this particular instruction, we are going to take a look on the INT. So INT, interrupt instruction with type number. So basically it is a two byte instruction. So the first byte provides the opcode, and the second byte provides the interrupt number type number. So there are 256 interrupt types under this group. So the execution includes the following steps. So first, the flags register value is pushed to the stack, okay, stack. And then CS value of the return address and IP value of the return address are pushed onto the stack. So IP, so from there, the IP is loaded, and from the content of the word location, type number will times with 4, and then CS is loaded from the content of the next location. Therefore, interrupts the flag and trap flag are reset to 0. So the starting address for type 0 interrupt is 0000000H. For type 1 interrupt is 00004H. Similarly, for type 2 is a 00008H, and so on. So the first 5 pointers are dedicated interrupt pointers. In example, so type 0. So for type 0, interrupts represents division by 0 situation. For type 1, interrupts represent single step execution that during the debugging of a program. Type 2 is interrupt represents non-masketable NMI interrupt. Type 3, interrupt represents breakpoint interrupt. Type 4, interrupts represent overflow interrupt. So the interrupt from type other than this 0 to 4, we have interrupt type from 5 to type 31, which are reserved from other advanced microprocessor, and interrupts from 32 to type 255 are available for hardware and software interrupts. And last but not least, we will go through instruction 5, which is the program execution and transfer instruction. So basically, for this instruction, it is used to transfer or branch the instruction during an execution. So two types of branching instruction. So, we have unconditional branch as well as conditional branch. So let's take a look at the first one, which is the unconditional program execute. So these are the execution transfer instruction. So we have the opcode of CALL, and the operand is address. The description will be used to call a procedure and save their return address to the stack. So after that, we also have the RET, no operand, and it is used to return from the procedure to the main program. We have JMP, the operand is address, used to jump to the provided address to proceed to the next instruction. Next, we got loop, and the operand is address, used to loop a group of instruction until the condition satisfied. In example, Cx is equals to 0. So for next, we have conditional program execute. So these are actually just a little bit of program execute that I would like to put in, but there are actually more. You can refer to the reference book. there are more opcode, operand, and what they are used for. So over here, I'll just go through a little bit. The opcode, if the opcode is JC, the operand is mostly goes to the address. So it is used to jump if carry flag CY equals to 1. Meanwhile, JNC used to jump if no carry flag CY equals to 0. For GE slash JZ used to jump if equals to 0, if equal or 0 flag ZF equals to 1. If JNE and JNZ, it used to jump if not equals to or 0 flag equals to 0. JO used to jump if overflow flag OF equals to 1, and JNO used to jump if no overflow flag OF equals to 0. So for this following conditional and unconditional, the address can be specified directly or indirectly. So it depends on the CF, ZF, OF, PF, SF, and CX. So for CF, if the CF is carry flag and ZF is 0 flag, OF overflow flag, PF parity flag, SF is a sign flag, and CX is the register. So basically that is what we have to know for the program execution and instruction transfer. Okay, so that's all from me. I hope that my video could help you to understand and give you a little bit more about the insights of the assembly language instruction. And yeah, thank you very much for watching.